Hello, my name is Stefan and I will tell you about the fatigue limit assessment of interacting small defects by cyclic R-curve analysis. So the defeat limit I will define as the stress range that a specimen endures for 10 million load cycles. The Kitagawa-Takashi diagram shows us the degradation of the fatigue limit with the presence of defects of a certain size. The limit curves come from fracture mechanical aspects of short crack growth, where we have two limits, the intrinsic threshold and the long crack threshold, which separate this diagram into a region of no damage, non-propagating cracks with the buildup of crack closure as a crack grows, and the failure above the long crack threshold. So we can put defects of different sizes into this diagram, a smaller defect, a larger defect, or a coalesced hull, a convex hull of two smaller defects. But where would these two small interacting defects lie with respect to effective size and the fatigue limit? That's a problem that has been investigated in numerous ways, but my approach would be to assume crack-like defects, perform a short crack growth simulation and extract geometry factors and interaction effects onto the fatigue limit. I removed most of the slides on literature survey. Just to summarize, there have been numerous investigations, experimental based, stress field based on void-void interactions, crack-crack interactions, or crack and void interactions, and most of them in a more qualitative or quantitative way result in the interaction effect that when the distance between two cracks is smaller than the smaller one, or two flaws is smaller than the smaller one, then you have to consider strong interaction effects. The other keyword in my topic title is the cyclic R-curve analysis. This is to find an equilibrium point between the cyclic R-curve and the evolution of crack driving force as the crack grows larger. And there we can find a point of maximum non-propagating crack dimension. To wrap this up, I want to state that most of the research deals with a sort of static analysis of interacting defect configurations, and also in the cyclic R-curve analysis, mostly constant geometry factors are assumed. And I want to refer back to my solution approach to perform a dynamic short crack growth simulation. The simulation is performed using the analysis software Frank 3D, where we can insert a crack into a non-cracked specimen. It does some remeshing, utilizes standard element solvers, and computes stress intensity factors along crack fronts. It supports various crack growth routines and also some Python API points. But what it does not handle is short crack growth, so a partial arrest of the crack front. And that's why I'm only utilizing the static SIF analysis of each crack point and implemented the short crack growth simulation in some custom Python scripts. I won't talk anymore about the simulation intricacies because of time constraints. And I also have to make one disclaimer. Just before this conference, I discovered a bug in my code which interprets at a certain point the R-curve in a wrong way, but which result in some errors. But the R-curves are still bound by the intrinsic and the long crack threshold limits, so the errors are bound. I am in the process of rerunning the simulations, so the following results will change slightly, but not in a too severe way. And where do these two R-curves come from? That's from the material characterization. I'm looking at an aluminum alloy that was SLM printed and stress relieved. I performed a tensile test, which shows a tensile strength of 250 megapascals and a fairly ductile behavior, and some crack propagation tests. Those show some variance, which I make use of by fitting two different crack resistance curves for the same load ratio, and therefore we can analyze the effect of these two different crack resistance characterizations on the simulation results. The simulation focuses on on circular defects. I'm simulating a single defect, the interacting defects, and the convex hull of those. for crack sizes between 0.1 and 2 millimeters, and distance between cracks of 1/4 to 3 times this crack radius. Here you can see the whole test matrix or simulation matrix. And here I have an exemplary simulation result. We are searching for the non-propagating load scale limit of maximum non-propagating crack formation, which means we are looking for a load scale factor between the intrinsic crack growth threshold and the long crack growth threshold. And for the results, we are looking at, for once, at the maximum non-propagating crack formulation, which would be sigma 3 in this diagram. And for the geometry factor evaluation, we are looking at the load scale factor 1 megapascal above this. So we get the through propagating crack and the geometry factor evolution until the cracks actually coalesce. The evaluation is done along the interaction axis of these two defects. And here I have the geometry factor results for an example for you. What we can see is here down we have the single defect. Those corresponds pretty constantly over the whole crack propagation length to the one of a circular crack. And the interacting cracks show two effects. For once, a shift to a higher geometry factor, and then a rising geometry factor as the cracks grow closer to another. I have to note that my geometry factors are only parameterized with the three geometrical parameters: the crack size, the distance, and the crack growth increment. So implicitly, I'm encoding both the cyclic crack resistance curve and the applied load level at this through propagating stress into my geometry factor results. Speaking of this dependence of load scale dependence, I present to you some results for the identical material, identical geometrical configuration, but simulations performed at different load scales. So the crack will evolve slightly differently depending on the crack front activation with respect to the R curve. So for higher load scales, I get slightly higher, I get consistently, but slightly higher geometry factors. This points to another difference in a static assertions and the dynamic crack growth simulation, considering short crack effects. But there are also influences of the simulation setup, because a higher load scale factor means less interference with the cyclic R curve, and therefore a slightly more, definitely a more stable simulation. To summarize the result of geometry factors, I plotted for all of the investigated geometry combinations the geometry factor trajectories for the crack growth, and we can extend this to a three-dimensional plot where I fitted the surface, and also you can see the red line. That's the geometry factor for the initial configurations of the cracks before they start growing. The second result are the interaction factors. Here I normalize the resulting non-propagating crack load scale level over the one that results from the single crack. Adding some color coding, we can clearly see the single cracks are normalized to 1. The convex hull lie here, and for the interacting cracks, we can come to similar results like defined by Murakami and or also Aman. That's when the distance between cracks becomes smaller than the diameter and radius. We get increasingly severe interaction effects. That can also be plotted into a three-dimensional diagram and fitted with surfaces, but that's not that easy to visualize if you can't manipulate, twist, and turn this diagram. So that would basically be the main results of my investigation: the geometry factors and the interaction effects. As we still have some time, I got some outlook. So as I mentioned, I got some simulation to do, so the results will slightly change. I started some experimental verification, which I will talk about after this outlook, because it's just in the initial stages. I want to do some comparative investigations into theory of critical distance evaluations of the interacting of the void crack interactions, and also energy density evaluations. I would like to utilize the evaluated geometry factors to apply a cyclic R curve analysis for an arbitrary material, and there I hope to, because the taken R curves T2, because of my failure in my code, they are fairly similar once you normalize them to the long tracks threshold. They're fairly similar, but you can take an arbitrary R curve, and therefore I hope to really distinguish the size effects of the interacting tracks and the length scale dependence of the cyclic R curve. Then the whole results could be integrated into a sort of multidimensional Kitagawa-Takahashi diagram. And I'm also in the process of extending the dataset to interactions of two differently sized defects. On to the experimental application. I talked about SLM printed aluminum alloys. So you can manufacture a circular defect, a void, fairly easily. I decided to have the laser directly trace the contour that I designed. So I added an offset for the accounting for the melt pool size, and that results pretty much dead on into the designed dimensions. Here you can see a burst fracture reference specimen, and below there's a reference study of different crack separation distances. And here are some initial experimental results. They follow the, we have a single defect, two defects at the distance of 1 millimeter, and two defects of 2 millimeters, and two defects at the distance of 1 millimeter. The defects are of a radius of 1 millimeter. And I performed cyclic tests running out at 10 million load cycles, and stepped up the load level, and we see the expected relation. Although the predictions would say that the 2 millimeter distance would need to lie closer to the single defect than it does to the closer lying interacting defects. Okay. The one interesting observation here is that the results lie fairly high above the predictions. Even on the conservative or non-conservative assessments of using the long track threshold onto the initial track size for the single defect, we arrive at, for the different long track thresholds, we arrive at lower load scales than we observe in the experiment. And that partially has to do with the conservative assumptions of the simulation setup that we have, the most severe defects, which are cracks. They are growing simultaneously. And in the experiments, we have deviations from this. That is, for once, possibly effects of the notch sensitivity. We observe local crack initiation instead of the cracks becoming directly, the voids becoming directly cracks. Environmental effects due to the protective atmosphere in the voids, and also various effects of the SLM printing process. And there I'm just going back to my results, and that would be it.